Okay, if there were one, we go to that back corner.
So we're going for that back corner.
Right.
We don't hide that little font.
Okay, z-scores and the standard normal distribution. So the problem with the normal distribution is it's got all kinds of different numbers for the mean and the standard deviation, right? So we saw, excuse me, we saw one that had a mean of 65 and a standard deviation of 4. And that's different from one that has a mean of 63 and a standard deviation of 3, right? So they all become different distributions. So what we want to do is standardize them and get this what's called a standard normal distribution. So a data value's corresponding z-score is the number that shows where the data value is in relation to the mean of the data, right? In terms of the number of standard deviations. So in terms of the number of standard deviations. So a z-score is a number of standard deviations away from the mean, in terms of the number of standard deviations. And what it allows us to do is standardize any distribution. So if you're comparing diploma scores in the province, you know, the Math 30-1 exam is going to have a different mean and standard deviation than the Math 30-2 exam, than the English 30-1, than the English 30-2, and so on. So if you want to compare your performance on different exams, what you're really looking at is, how did I do in this exam relative to everybody else, not what was my mark. Okay, and there's certain score or exams, you heard the SATs or the LSAT or the MCAT, any of those guys, they're standardized tests. So what they want to do is make sure that from year to year when they report results, they're reporting the same results, right? Not different ones. So maybe one test is easier than the other, but what they'll do is measure it in terms of relative to everybody who wrote it that year, how did you do? And that's using a standard normal distribution. So if a data value has a z-score of 1, then it is 1 standard deviation. So it works positive and negative. The mean has a z-score of 0, it's in the middle. 1 standard deviation above will be 1. If a data value has a z-score of, you put -1, then it is 1 standard deviation below the mean. Okay, so what does that mean? What does that look like? So let's take a look at this data set with a mean of 12. So let's sketch it out. Mean is 12, standard deviation is 3, so what's 1 standard deviation above? That's 12, and standard deviation is 3, then this is 15, and then 18, and then 21. And going down this way, what will we get? 9, and then 6, and then 3, right? And we can match that up with the chart that we have, right? And you're given that chart, be on the formula sheet, right? So the 34.5%, 34.5%, 13.5%, right? So you can say, all right, so a data value of 18 has a corresponding z-score of, so down here, let's do the z-scores. So this is a z-score of 0. The mean has a z-score of 0. 1 standard deviation above, 2 standard deviations above, 3 standard deviations above, 1 below, 2 below, 3 below. Okay? And then you would have seen that written as like mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. Right? And so what you're looking at, if you're looking at the mu plus sigma stuff, you just look at the number in front of the sigma, right? So there is nothing there, right? So that's 0. That's plus 1, plus 2, plus 3. So that corresponds to a z-score of plus 1. Okay, so 18 has a z-score. Yeah, well, 18 has a z-score of.
Can we yell at him? Can I yell at him?
No. So 18 has a z-score of what? 2, right? It's 2 standard deviations above the mean, has a 2. 9 has a z-score of -1. Data value of blank would have a corresponding z-score of -2. 6, right? So having the table there, or drawing the diagram is kind of handy, right? So you might want to do that on a question. Blank would have a z-score of 4. Okay, we don't have that here, but where would we go to get a z-score of 4? 24. Data value of 24. That's because almost nothing is out there, right? When you get like 4 standard deviations above or below. Data value of 13.5 would have a corresponding z-score of. So 13.5. That's kind of there, right?
Or 1.5.
Which one? 0.5 or 1.5? Sorry?
1.5, right?
Okay, so what's 12? 12 has 0, 15 has 1.
All right.
Okay, so 0.5.
Sheesh.
And what would have a z-score of minus 1.5? So think we're in here. 6, 9, 7.5, right? So 7.5. So it would be handy if we had some kind of a formula, right? We're going to come up with one. If the data value is below the mean of the data set, then the z-score is negative, and if it's above the mean, then it's positive. Z-score formula, here it is. Okay, so if x is any data value, then x is equal to mu plus z times sigma, right? Let's go back. So x is any data, so we have data value of 15. 15 is equal to 12 plus 3, right? Sigma, so mu plus sigma. Mu plus 2 sigma, right? So x equal to mu plus z times sigma. So the z-score is x minus mu over sigma. So what you do is you say, how far away are you from the mean, x minus mu, right? Now if x is above the mean, that'll be positive, right? If x is below the mean, that'll be negative. Okay, so if we think the mean was 12, 9 minus 12 is negative 3, and then you divide by 3, gives you negative 1. Okay, so it's a way to convert. And that means it gives us this standardized thing. Okay, so the mean running time for a 10-kilometer race was 41.3 minutes for the men with a standard deviation of 3.2 minutes, and 45.2 minutes for the women with a standard deviation of 4.6 minutes. Johnny ran the race in 39.2 minutes, and Janine ran the race in 42.7. Who performed better compared to their same-sex peers in the race? Right? So it's not fair to compare the men and the women in terms of the actual number. It's fair to say, all right, compared to all of the men, how did Johnny do? So what we need to do is get Johnny's z-score. Okay, so what we will do is we will say z for Johnny is equal to x minus mu over sigma. Okay, so write the formula down. You're going to get it. It's on the formula sheet. So what is Johnny's x value? $39.2, right? So the x value is the score associated with a particular person. The mean for the man was 41.3. And the standard deviation for the men is 3.2. Okay, so to do this, I'm just going to pause because we've got to get the calculator. Okay, so using your calculator, you need to put brackets around the top, right? Otherwise, what you'll do is you'll go 39.2 minus 41.3 divided by 3.2. It'll do the division first and then the subtraction, right? And you'll end up with, I mean, let's do it wrong first just so you can end up with a really weird number. 39.2, so if you enter it this way, minus 41.3 divided by 3.2, 26, right? There is no such thing as a z-score of 26.9. I mean, there is, but it doesn't happen, right? Remember, z-scores should be between 3 and negative 3. Also, we know that his time was less than the mean, so he should have a negative z-score, right?
Yeah.
Okay, so we're going to go bracket 39.2 minus 41.3 bracket divided by 3.2. Okay, so we get negative 0.65625, so equals negative 0.6. Now let's go with, what was it, 656? So let's go with 2 decimal places. So in this case, being below average is good, right? Because you're running a race, so if you're below the average time, it means you're faster. being below average on a test, not so good, right? Because, okay, and then the z-score for Janine. So x minus mu, write the formula down every time you use it. So Janine's time, Janine ran the race in 42.7 minutes. The mean for the women was 45.2, and the standard deviation was 4.6, right? So who were more spread out, the men or the women? The women, right? Higher standard deviation says the data is more spread out. Okay, so slide this over here. Okay, remember you need brackets, right? Or do it this way, 42.7 minus 45.2, enter. Okay, it's negative 2.5, divided by 4.6, so divided by 4.6. And we can see it's negative 0.54, negative 0.54. Okay, so relative to their peers, who did better? Johnny, right? Because the lower it is, the further away from the mean he was, right? So this is placing him on the distribution, right? And it's also placing her. And we're placing them on the same distribution, right? The standard normal distribution. Mean of 1, standard deviation, or sorry, mean of 0, standard deviation of 1. Okay, so Johnny performed better relative to his peers. Okay, questions?
Yeah, hold on.
Observations, comments? Yes. What? So, there was some stuff up front. Did you take it with you?
Like a lanyard too.
Well, remember the notes will be, you can just print off the notes, right? Okay, so this will be stored as a PDF. Wow. Shoes here. Got an alternate pair of shoes just in case. Johnny was told his Z-score for a recent mark on a test was 1.23. Okay, positive Z-score on a test is a good thing, right? It means above average. Okay? And the standard deviation was 8.5%. If the actual mark on the test was 72%, then determine the class average. Okay, so we got a formula, right? Z is equal to x minus mu over sigma. Which of those is the average? The Z, the x, the mu, or the sigma?
Let's be real. Too much. They're 6.0.
Average is mu.
Right?
So we are given the recent mark. We're given his Z score. That's Z.
Yes.
And the standard deviation was 8.5%. That's sigma. His actual mark on the test, that's x.
So we have to rearrange.
Okay, so we need to rearrange formula. Yeah, so we could do that. We could just rearrange the formula. So let's multiply both sides by sigma. Okay, we're trying to solve for mu. We want to get mu by itself. So the easiest way to do that is to move the mu over here. So it's negative. When it moves over to the left, it becomes positive. And then the Z sigma will be subtracted, right? It's positive, so we're going to have to subtract it. So now we've rearranged, right? Now you don't have to do that. You can just substitute into the original. So we'll do it both ways. So here's this. So mu. So now we've got the thing we want to find. The x is 72. The Z score was 1.23. And the sigma is 8.5. Okay, so 72 minus 1.23 times 8.5. Okay, you can just enter that. There's nothing tricky here. There's no long fraction bar or anything. Hit enter. And we get 61.545. Okay, so the class average was 61.5%. Okay, if you go here, you do it this way, right? You put the 1.23 in, that's your Z. The X is 72. minus mu, which we don't know, and the sigma is 8.5. Okay, so to solve this, you're going to start by multiplying both sides by 8.5. Right? So 1.23 times 8.5 is 10.455. Don't round. Okay, so you say 72 minus something is 10.455, so we just kind of interchange those, right? So mu is the 72 minus the 10.455. Okay, and after rounding, you get 61.5. Okay? Questions?
What?
And we're having a lockdown.
I see that
Shortly.
And
Finding percentages given Z scores.
Lockdown, lockdown.
I got it.
We're in the tail end of a lockdown, so if you hear bells in the background, that's why. So Mark and Mitchell ran the same 10-kilometer race as Johnny and Janine. Mark's Z-score was negative 0.75. Mitchell's Z-score was 0.56. If the race times for the men were normally distributed, determine the percent of male runners with times between Mark and Mitchell's. Okay? No, Mitchell. So 0, 1, 2, 3, negative 1, negative 2, negative 3. So Mark's Z-score was negative 0.75. It's going to be about here. And Mitchell's Z-score was 0.56. It's going to be about here. And what we want is this area. Okay. So in order to solve these next set of problems, we're going to want to sketch out a normal distribution. We're going to want to list the Z-scores, right? We want to go from negative 0.75 to 0.56. There's a calculator function that lets us do that, right? And really the only way we can do this, because it's not between 0 and 1, which we know is 34.5%, right? So it doesn't match up with the chart that we've been using with the percentages.
Do it.
No, they're not Nikes, are they?
Mr. Yamamoto.
Yeah, so you can't just do it. Yeah, I know, but what can we do?
Right.
I'll speak between the brain meters. Okay, so we can't match that up with the standard normal distribution, right? Which we can with some questions, and it is on your formula sheet, so you might be able to match it up. That's easy. So you're going to use a function called normal CDF, okay? And I'm going to show you where that is. And to use normal CDF with Z-scores, what you do is you put in the low Z-score and the high Z-score. So the low Z-score is negative 0.75 and the high Z-score is 0.56. Okay? Now normal CDF can also be used with raw scores, like if they actually gave us the times, but we're not doing that one now, we're just using Z-scores. Okay, so here's how it works. I'm gonna turn this thing on. Turn on. Oh, crap, where did it die? Okay. So here's what you do. You go second function vars takes you into the distribution menu. This is not. Oh, okay. Okay, so second function and then vars. That'll take you into the distribution menu.
Varsity.
Vars, yeah, varsity.
One?
Okay, we want normal CDF, which is 2. Okay, so you can either push 2, or you can arrow down to it and hit enter. Now, depending on the calculator you have, so if you have the 84 with the new software, you're going to see this. So how many people see this? I mean, not here because you should all see this, but in your calculator.
Yeah.
Okay, how many people just see the word normal CDF and then a bracket?
Yeah.
Okay, that's fine. Okay, fine. So here's what you do. if you see this, our lower is negative 0.75. If you just see normal CDF in a bracket, put in negative 0.75. So either you see this, like if you, on your calculator with the 83, this is exactly what you want to enter. Negative 0.75, comma 0.56, close parentheses. Okay? So any calculator that doesn't show this display, on this one, our upper is 0.56. Now, what the calculator does is it defaults to a standard normal distribution, so it says the mean is 0 and the standard deviation is 1. On the 83s, or the other calculators, you could enter negative 0.75, comma 0.56, comma 0, comma 1. So it defaults to that, just like this calculator has defaulted to that. You don't have to enter it, okay? If you're using a standard normal distribution, right, if you're using z-scores, this is good enough. Okay, so we just hit enter because we have a 0 and stamp hit paste. Okay, and what it does, so this is what you guys are going to see, only you can close the bracket after the 0.56. Hit enter, and it gives you the area. So the area under the standard normal curve is 1, right? Because it's 100%. Everything is taken care of. Everything is accounted for under the standard normal curve. So it has an area of 1. If we want to get this as a percentage, then we multiply by 100. So just go times 100, enter, 48.56%. Okay? And oftentimes we'll just give it to 2 decimal places, right? So equals 48.56%. So it tells us almost half the people had times, right, between Mark's time and Mitchell's time. Almost half the people. Less than Mark's time. So Mark's z-score was negative 0.75. And this time we want the area less than Mark's time. So the reason we put one of these for each question is because you should draw one when you're working it out. Just sketch out a normal distribution. On that distribution, shade the area that you want. Okay? So we're going to do normal CDF. Now, we need a lower number, and there's a special number we use for the low number. Okay? And it is negative 1E99. Okay? So that translates to negative 1.0 times 10 to the 99th, right? Which gives you 99 zeros. E negative 99.
But on the calculator, which
No, E negative. Yeah, okay, I'll show you how to get that. Okay, so calculator out. Now, second bars into the distribution, number 2, normal CDF, lower. Okay, so it's just going to go back to what I had. So you go negative 1 E. The E is second function comma. Okay, so second function and the comma gives you the E, and you put 99. So what you're getting is negative 1 times 10 to the power of 99, which is negative 1 and then 99 zeros after it, which is a really, really big negative number, right? Our upper value is, so what we're saying, normal CDF says, give me the area between negative 1e to the 99 and negative 0.75. And so your normal CDF, okay, and you don't need to put, so paste. Okay, so those of you without, yours will look normal CDF bracket negative 1e99 comma negative 0.75, and then you can close the bracket. Okay?
You don't do the 0, 1.
Yeah, so if you're doing a z-score, you don't have to do the 0 and the 1. Okay? So it defaults, just like it did. You saw the menu and it came up with a 0 and a 1 already in there, right? Okay, so that's what it'll default to. Okay, then we hit enter and it calculates it. 0.2266, you want that as a percent. So times 100, and we get 22.66%. Okay, 0.662, so it's going to round to, right? If you have problems with rounding and you know you got to round to 2 decimals, just go mode and go to float and set it to 2. More than Mitchell's time. So Mitchell had a z-score of 0.56. So put it about in the right place, okay? It doesn't need to be exact, but that's 0, that's 1, so 0.56 should be between them. More than is greater. So this is the area we want to find. So we set it up again with normal CDF.
Oh, we got caught.
Our low value is 0.56. What do you think we're going to use for the high value?
And then,
I don't know.
oh,
1.
E99.
Yeah, positive 1 E99. Okay? So if we're going between two given values, then we use them, right? And if there's z-scores, right? So they got to be z-scores. You go just 0.56 or negative 0.75 comma 0.56. Or we could be going below. Then our low value is negative 1 E99. Or we could be going above. Then our high value is 1 E99. Okay, so we go into the calculator. Second bars distribution, number 2. Okay, so this time my low is 0.56. My high is 1. Ryan, for crying out loud. Okay, lower is 0.56. The upper is 1 E99. Okay, now there is a way to do this with raw scores, in which case we change the mu and the sigma to match the raw scenario, right? Because your calculator can calculate the z-scores for you, right? It's got that formula, z equals x minus mu over sigma. Okay, so we paste. There it is. If you're using your calculator, you put the bracket after the 99. Won't make any difference. 0.2877, so times 100. 100 is 28.77. Okay, so we're going to put this on your formula sheet, right? It's going to say normal CDF, lower, comma, upper, comma, 0, comma, 1 for a z-score. Finding percentages giving, did we just do that? More than Mark's time. Or is this, oh, this is just more than Mark's time. Greater than Mark's time. Okay, so Mark's score was negative 0.75. So do this every time, right? Sketch out a little normal distribution and shade. More than is this way. So now you do normal CDF. Negative 0.75, 1 E99. Second distribution, number 2, normal CDF, negative 0.75, 1 E99, right? That stays the same.
How do you do the 1
1, second function, comma, brings in the E, and then put a 99. Okay, and we get 77.34%, right? I'm just going to 77.34%. Less than Mitchell's time. Mitchell had a 0.56. Less than Mitchell's time, there's 0.56. And we're going down. So here, maybe we write in the 1 E99, and here, negative 1 E99. So when you do normal CDF, you're going from left to right. Okay, you're taking your left number, negative 1 E99. So normal CDF. Negative 1 E99 up to the high number 0.56, and if you want you could put in the 0 and the 1. Okay, you don't have to, it'll default to that. Okay, second distribution, normal CDF, my low negative 1 E99, my high 0.56, mu and sigma are 0 and 1, paste, and enter. 71.23%, right? So again, just move the decimal over 2 and then round the last digit, so the 2 with the 6 next to it, 71.23. If you want, right, if we say, all right, look, you're always rounding, then go to float and go over to 2 and hit enter. And then I can quit, and then I can just go times 100. Whoops. To answer times, quit moving, times 100. Enter, and it'll round it for me, right? Okay, so if you ever difficulty in rounding, let the calculator do the rounding for you. Finding percentages given z-scores. Mark and Mitchell, did we do this? Oh, okay, so Mark and Mitchell ran, so this time we want percentages. This is just more of the same. Mark and Mitchell ran the same 10-kilometer race as John, blah, blah, blah. Okay, so it's the same scenario. Mark was faster than what percent of the runners? So what was Mark's z-score?
Mark's z-score was negative 0.75.
Okay, so let's mark that on here. Mark, huh? Get it. Now, are we looking for the below mark or above mark?
Well,
Yeah, so he's faster than, so Mark's Z's, okay, wait a second, the race times ran, Mark was faster than, so were the people below him faster than him or slower than him? People below him.
Faster.
They were faster. So do we want below 0.75 or above? We want above, right? So this is z-score of 0, right? So what we do is we take, when we do standard normal distribution, we set the average to 0. And we take everybody's score and we divide it by what we see. How far are you from the mean, above or below? We divide it by to turn it into a z-score. Now, if you're talking test marks, you want to have a positive z-score, right? Because that means you're higher than average. If we're talking races, you want to be below. So these guys here are faster. So we want this. Mark was faster than. We need the people who were above him, right? Like what percent of the runners were above him? Okay, so we go normal CDF. Okay, so let's write in the 1E99 here. Negative 0.75, comma 1E99. You could put in the 0 and the 1 if you like. It's not going to hurt. Okay, your calculator is going to do that depending on the calculator you're using. So what do we got? Negative 0.75, enter. 1. E99 and the 0 and the 1, okay? And we'll do some examples where it's not 0 and 1. And then hit enter. 0.77 times 100, right? Because all it's showing me is 2 decimals, and if I wanted this thing rounded, I actually have to do the times 100. 77.34%. Mitchell was faster than, okay, what's Mitchell's z-score is 0.56. Which way do we go, above or below? Okay, we want to go above, right? He's faster than. These are the people. People above have bigger time, larger than Mitchell's, right? Which is going to be a slower or a longer time. So normal CDF, 0.56, comma 1E99. Now, what I would do, or you just go, if you got the 83 or the 84, just go second function, enter, bring this back down and change that to 0.56, right? So you don't have to retype the whole thing. So let's see, I should be able to do that. I can go up here. So bring that down and edit it. So just showing you what you could do if you have an 80, whoops, too far. So it goes 0.56, 6, comma 1E99, right? So you know, we're doing the same kind of thing. The only number I want to change is the negative 0.75. 0.29, okay, times 100. I'm going to change my rounding. So mode, I'm going to go back to float. Okay, 28.77. Just put that there, 28.77%. If there were 5,000 runners, then Mark was faster than. Okay, so 0.28. So what we do here is we want to get an expected value, which I just taught in 30-2 yesterday, which means they already knew how to do that, right? Because you know how to do this. But I reminded them. So what you do is you just take the number of runners, so 5,000, and multiply it by the actual number that's in your calculator, right? So I want to multiply it by this number. So let me just go back and get this number. Okay, so there, it's sitting in my calculator, right? 0.2877. If I need to express that as a percent, I could just move the decimal over 2 and just look here and say it's the 3 next to it, so it's 28.77. If I want to know of 5,000 people, I just go times 5,000. So it'll bring that number down, and we say 0.2877, right? 39682 of the people, right? That's the probability. It's like the beating of a heart. Is 1,438.69841 people. So it's people. What are we going to do with people? We're going to round them, right? Mark was faster than. Hang on, am I doing Mark or Mitchell? Oh, the 0.2877 is Mitchell, so sorry. This needs to go down here. Okay, sorry, just drag that down there. And we've got the 1438.6, so we'll call that 1,439 people. So 1438.6. Actually, it doesn't matter what's after the decimal. If it's more than 1,438, then we're going to say it's 1,439. Okay? So regardless, if it's 1438 point anything, we go to 1439. Mark, okay, Mark's number was this one, the 77.34. So I had to go back here. I'm going to go get that number, right? Because it's sitting up. And you can do this on yours, no matter which calculator you have. You can always bring down the. Okay. So I want this calculation, right? So just arrow up to it and then hit enter. It'll bring it back down. Hit enter. So it recalculates the number. Go times 5,000. And we get 3866.8. So 386.7. Okay, so they're people, so we don't round them, so it's 5,000 times 0.7734 ... Don't round that number either, right? Okay, remember, any intermediate calculations you do, we don't round the numbers. Okay, sorry, do you still need that percent? Okay, so there's the two numbers. Okay, so take their normal CDF, right, which comes out as a decimal, and then multiply that by the number of people, and you'll find out how many of those people. Right, so if there are 5,000 runners, he's faster than 3,860, and Mitchell's only faster than 1,439. Okay, enough with the dots. Finding z-scores given a percentage, right? So what we did is we said we've got two z-scores, or we've got a z-score, and we're going all the way to the bottom or all the way up to the top, and we could find percentages. What if we give you the percentage and say, fine, what's the corresponding z-score? Okay, so there's a different calculation, again using your calculator. So determine the z-score of a data value if 35% of the data. Okay, now here's how a normal distribution works. Underneath here is 100% of the data. Oh, thank God.
Oh my God.
It's done.
a normal distribution is symmetrical about the mean, right? So half the data, remember, normal distribution, you got the mean, the median, and the mode
Now over, please resume normal activities. Thank you.
all in the same place. Okay, so the mean, the median, and the mode are all in the same place in the middle. The median is the middle, so it says 50% of the data is below the middle, right, and 50% is above. So we want, if 35% of the data is to the left, so we're just going to put a number here, sketch this in, and say, this is 35%, but we need to express it as a decimal, so we go 0.35, okay? So we're going to take the area to the left of the z-score, right? We're trying to figure out what's the z-score here, right? We know it's negative, right? Because if it were 0, the z-score were 0, that would be 50%. Okay, here's the calculation we use. It's called inverse norm, INV norm. An inverse norm is used with the area to the left, so 0.35. Now, that's all you need to put in if you've got an 83 and you're doing areas, right? You're doing percentages, because it will default to 0 and 1. And I'll show you on this calculator what that looks like. So in this calculator, second function bars into the distribution, number 3 is inverse norm. Area, got to be a decimal, 0.35. Mu and sigma, 0 and 1. Okay, so on your calculator you could enter, you're going to see, some of you will see inverse norm bracket. You put in 0.35. You can put the 0 and the 1 in or not. It'll default to that, right? Just like this calculator did. So we go enter, 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 paste. Okay, so either yours says inverse norm 0.3 or 0.35, and you can close the bracket, or you can put the 0 and the 1 in. Hit enter. That's your z-score, negative 0.385. So we'll call that negative 0.39. So z equals negative 0.39. Okay, so that's a z-score. Determine the z-score of the data value if 24% of the data is to the right. Okay, so we know that it's 50% from here over, so 24% to the right is going to be this, and we'll call that 0.24. Now, inverse norm, this number is the area to the left. So I don't want this 0.24, I need this area. It adds up to 100, so it's 1 minus 0.24. Okay. Now you may or may not.
Yeah.
Were you just outside the building when it happened, or were you just stuck somewhere? Okay. Well, there are worse fates than sitting here listening to bells. Okay, here's what I'm going to enter, right? I'm going to say, all right, I need the area to the left, and I know the area to the right, so I'm just going to go 1 minus 0.24. Let the calculator do it for me, right? You could calculate it if you want, right? It's 0.76. And then you could put in here 0.76. But you don't need to, right? You could say, all right, the thing about inverse norm is it needs the area to the left. And I have 0.24. I have the area to the right. So I know that this area here is 1 minus this area here. Okay, so bring up the calculator. I'm just going to go second function enter to bring that down. And I'm going to change this to 1 minus point, and I'm going to go insert 0.24, and I'm just going to show you, I'm just going to delete the 0 and the 1. So that's all you're going to enter, right? 1 minus 0.24. Hit enter. 0.706. Remember, that's not a percent, that's a z-score. So the z-score is 0.71. Right? This z is equal to 0.71. So we're giving it the percentage, right? But not as a percent, as a decimal. We're giving it the percentage, and we're working out the z-score. Okay, questions? Moving on, let's finish this off. Were you stuck in the building somewhere?
No, like I literally walked in and was like, this is a lockdown. I was like, okay, what would a smart person do? So I went to the library.
Jack ran the same race as Johnny and was faster than 40% of the other male runners. Determine Jack's Z-score and his actual running time. Okay, so Z-score, we're going to use inverse norm. He was faster than 40%, right? So that means this is 40%, which is 0.4. This is Jack's Z-score. Okay. In order to calculate Jack's Z-score, we're going to do an inverse norm
Is that closer than
on 0.4. Okay. And that's all we need, right? Because he's faster than 40%.
Wait, by norm do you mean the CLF? Normal CLF?
there's no normal CLF. It's normal CDF. Actually,
CDF.
I put Jack in the wrong place because I'm mixing up faster and slower.
Okay.
So Jack was faster than 40. So Jack was faster than 40% of the other male runners. So that means that this was faster than 40%.
What happened yesterday? Right? It's like it's gone.
Okay, so remember, over here is slower, right?
Yeah.
Okay, so he's faster than 40%, so we got 40% over here that are slower than Jack. So I put Jack on the wrong place. This is Jack's Z-score. What's this area here? So either you can calculate it, right? So I want to do an inverse norm on 1 minus 0.4. Okay, which is, so this area here is 1 minus 0.4, and you can calculate that. It'll be 0.6. Or you can just enter it. Okay, so you do inverse norm 1 minus 0.4, or you can do inverse norm 0.6. So second distribution, 3, inverse norm. I'm just going to put 0.6. Mu and sigma will be 1 and 0. Paste. And we get 0.25, or yeah, so this is his Z-score, right? So Z equals 0.2533. And more, right? Because I don't want to round that, because I'm going to use it to calculate his actual running time. Now, his Z-score, if I'm going to round it just for telling you what it is. So Jack's Z-score was 0.25. Okay, so I'm going to round that just for presenting the number to you. Round it to the nearest hundredth. His actual running time. Okay, so we got to use the formula. Z equals x minus mu over sigma. We know Z. What are we looking for? X, mu, or sigma? So are we looking for the standard deviation? Did it say, what's the standard deviation?
No.
No.
It's the Z-score. It's
Okay.
the actual running time.
Which is what? X.
X.
Yeah. Remember, so in that formula, Z is the Z-score. Kind of obvious, right? Mu is the mean, because we're doing mu as mean for this time. Sigma is the standard deviation. We're using sigma as standard deviation. So X is the actual score, right? So we're trying to find X. So we can do a little rearrangement, right? Z sigma is X minus mu. So X is equal to Z sigma plus mu, right? Move this over. Add it to both sides, right? And isolate, right? So we're trying to isolate the X. So X is equal to Z sigma plus mu. Okay, we know the Z. We're just going to pull that out of our calculator. So X is equal to 0.2533 times sigma. Okay, now sigma, that's the standard deviation that they gave us way back when, right? And that sigma for men was wait a sec. Yeah, sigma for men was 3.2. Okay, so 3.2 plus mu, and the mean for men was 41.3. Okay, so these numbers come from the page back. Okay, back in the original calculation. Okay, so I want Z. I've got Z right there, right? So I want Z times sigma, so I'm just going to go times, right? Answer pulls down that number, times 3.2 plus 41.3, which was the mean for the men, and we get 42.11. Okay, and how will we record that? 42.1. So we'll say 42.1 minutes. Okay, so if you look at what happened, we know that Jack was in the same race with the guys. We know that he was faster than 40%. Okay, remember, this is slower to, this way is slower, and this way is faster. So he was faster, so 40% were slower than him, so we've got the 0.4 here. We need to get his z-score, right? Because we want to use this. The only way we have of finding his actual time is to find the x value. So we put in the area to the left, right? Either as 1 minus 0.4, or we do that calculation, get 0.6. We get his z-score, put it into the actual running, or into the z-score formula, and work out the x value. Okay, and then we're going to do the same thing with one of the women running. So Jaspreet ran the same time as Janine and was in the bottom 25% of all the female runners. If the women's race time, so she's in the bottom 25%, which puts her, whoops, just erase that. Puts this as 0.25, right? That's where she's sitting. Okay, the bottom 25%, which is at the top of our thing because slower is to the right. So watch out when, if these are marks, then to the right is good, right? It's above average, okay? So a positive or negative z-score doesn't mean good or bad, right? A negative z-score is good if you're running a race because you're below the average time. A negative z-score is good if it's a golf score because you're below the average score, right? Some things we want to be below. A negative z-score is not so good if it's a test mark because it says you're below average, right? A positive z-score, so if these are test marks, to the right is good and to the left is bad. If these are golf scores or running times, then to the left is good, right? Slower or lesser time is good and a higher time is bad. Okay, so for her z-score, we're going to do inverse norm on 0.75. Right? So we need the area to the left. We need this area, which is 1 minus 0.25, or 0.75. We're going to keep that number in our calculator. Actual running time, remember, x is equal to z sigma plus mu. We can just use the formula again, right? We developed it in the one above. We're going to use it again. Okay, so this is z, right? The z-score is equal to this, right? So it's inverse. Work first time, come on. So inverse norm, so I'm just going to go up and grab it and pull it down. And I'm just going to go over here. So I want 0.75, and I'm just going to delete everything. Delete. Right? So I can give it inverse norm 0.75, right? If we're working with z-scores, that's fine. Right? If we're working with raw data, there's different numbers, right? It operates a little bit differently, and we'll see that in days to come. So our z-score is 0.6744. So I'm going to report that as z is equal to 0.67, right? I'm going to give you the z-score rounded to the nearest hundredth. And then we're going to take that and use it here. So we need to fill in some numbers, right? We've got our z-score. Now, the sigma value is for women, right? So we go back to the original and we see that our sigma for women is 4.6, our standard deviation, and the mean was 45.2. Okay, so there's Z, so I'm just going to go times 4.6 plus 45.2, enter, and get 48.3. So we'll just go with 48.3 and say Jaspreet's running time was 48.3 minutes. Okay, give you a chance to copy that down, and we'll just look at the rest of it, which is just showing you how to use the thing. Okay, and when we look at that, I'll tell you what's on the formula sheet, right? So you'll know, okay, good, I don't have to memorize this. Okay, so again, keep in mind what we do, right? So you're going to need to practice a few of these, right? You're not going to sit down on a test and here's the question, you're going to remember that, right? Well, maybe what's his face there might remember it. And, you know, well, I don't know if he can remember it because it's not like he's seeing it at all.
Right.
You'd actually have to have seen it for the first time to remember it. Yeah, I know.
Oh my
It was a
gosh.
lucky back. It was a step back.
Well, we'll see how well that works for you.
I got
Okay, in general, the normal CDF function finds the percent between two, okay, expressed as a decimal, right? Expressed as a decimal. So it really finds a decimal, and then you can change that to a percent. Between two z-scores, given the mean of 0 and the standard deviation of 1. Okay, how do you get there? Second function distribution, normal CDF. Now either you get the menu, like you've seen up here, or you get an open parenthesis, right? And then you put in lower z-score, comma, upper z-score. Followed by the mean and the standard deviation if you want, but they will default to 0 and 1. Multiply that by 100, you get the percentage. Okay, remember, a low. So on here, the left bound is -1 E99, and the upper is 1 E99. Okay, so there's no decimal in there. -1 E99. So if you're using a left bound, it's everything below something you use from -1 E99 up. Okay, if you've got two numbers like the -0.75 and the 0.56, like we're looking for something in between two z-scores, then we go low to high. Okay, and if you're looking for everything above something, then you go from the low z-score up to 1 E99. Okay, so is this on your formula sheet? It says for z-scores only, pretty much. Okay, it doesn't say second function distribution, but it does say normal CDF. And it says LB, comma UB, which is lower bound, comma upper bound, and then a 0 and a 1 for a z-score. And it also gives you the same for inverse norm. And then for inverse norm, for finding, in general, the inverse norm function finds the z-score. Okay, so you give it a percent, you say there's so many people, and it's got to be to the left of the data to the left. So if you know the percent to the right, you go 1 minus that number. Okay, it's got to be the percent left of the z-score you're looking for. So you take the percent to the left, divide it by 100 because it has to be a decimal. That's the input. You go 0 and 1, or not, right? Like you don't need them; it'll default to 0 and 1, and you'll get your inverse norm. Okay. I think we're done.